Let's get into graphing the functions of more complicated rational functions. Okay, we already know how to identify the vertical asymptotes or the holes. We discussed that. Vertical asymptotes are still found by the denominator. But now that we know that there is a different type of asymptotes or that we have slant asymptotes, we need to be able to determine whether our function has a horizontal asymptote or a slant asymptote and where they are located. Okay, and this is the table we're going to use to determine what kind of asymptotes we're working with. So for a rational function, y equals p of x over q of x, where p of x and g of x are polynomials with leading coefficients a and b, we have the following rules for horizontal and slant asymptotes. Okay, what we're going to be using is the degree of the polynomial to determine what kind of asymptotes we have. So if the degree of the numerator is less than the degree of the denominator, then we have a horizontal asymptote at y equals 0. Make a note, this is a horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, then we have a horizontal asymptote at y equals a over b. Remember, these are the leading coefficients of your polynomial. So you're going to divide them or simplify, okay? And finally, if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. You are going to have a slant asymptote, and the way we find this is by doing long division. So let's go ahead and do a couple of examples here on the next page to determine what kind of asymptotes we have. Okay, for A, we have x plus 1 over x squared minus 3. Remember, look at the degrees. It doesn't matter what your function says, all that matters is the degrees. The degrees come from the exponents of the variables, right, when it's written in standard form. So you can see in the numerator we have a degree of 1, and in the denominator we have a degree of 2. Because the degree of the numerator is less than the degree of the denominator, we know we have a horizontal asymptote. Where am I at? Down here. We have a horizontal asymptote at y equals 0. Okay. Looking at b, we have 3x squared plus 6 divided by 2x squared plus 1. You can see our degrees are 2 for both the numerator and denominator. So because they have the same value, we know that we're going to have a horizontal asymptote at y equals a over b. So where is a over b? A and b come from the leading coefficients of your polynomials. Okay, so this one isn't too hard to determine because it's already written in standard form, and we know that our horizontal asymptote is located at y equals 3 halves. You can leave it as a fraction, or you can convert it into 1.5 or 1.5. Finally, for C, we have x squared plus 6x plus 1 over x minus 2. Now, in this case, the degree of the numerator is 2, and the degree of the denominator is 1. This tells me that my numerator is greater than my denominator, and we have to find our slant asymptote by doing long division. Okay, so let's go ahead and set this up. We're still performing long division, so we have x minus 2 divided into x squared plus 6x plus 1, where x squared divided by x is x, right? Because x times x is x squared. Multiply the whole thing, x minus 2 times x. and we get x squared minus 2x. Change our signs, perform the operation. X squared minus x squared cancels out. 6x plus 2x is now 8x. Bring down the 1 and repeat. 8x divided by x is 8. Now multiply. 8 times x minus 2 gives us 8x minus 16. Change our signs. Perform the operation. 8x minus 8x cancels out. And 1 minus 16, or 1 plus 16 is 17. Okay, so 17 cannot be divided by x. We've done everything we can. Here is where your slant asymptote comes from. Your slant asymptote is the quotient of the division performed by the function. Okay, so in this case, we have our slant asymptote, and I'm just going to use SA to abbreviate, at y equals x plus 8. So it is an equation, right? And if you guys think about this, this is in the format of y equals mx plus b, because we have a y-intercept and we have a slope that we could use to sketch out a linear function or a diagonal line, right? That's a slanted line. All right, so now that we know how to identify the types of asymptotes that we have, let's go ahead and talk about graphing these functions. This is a multi-step process, okay? So I'm going to give you about, I think it's about 5 steps in order to graph the function. And we need to find the vertical asymptote, any holes, horizontal or slant asymptote, x-intercept, y-intercept, and then state the domain, okay? That's a lot. So looking at A, we have x plus 1 over x minus 2. Our first step is going to be to identify vertical asymptotes and any holes, if there are any, okay? So it's a linear function. You can see both of the polynomials are linear. We're going to start by identifying our asymptote. We have a vertical asymptote at x equals positive 2. You can tell that there's no holes because we don't have a common factor to cancel out. So we only have a vertical asymptote here. Okay. Second step is to identify horizontal asymptote or a slant asymptote. You cannot have both, it's one or the other. So looking at the degrees, because we have a degree of 1 in the numerator and the denominator, this tells me that we're going to have a horizontal asymptote at y equals a over b. And in this case, our leading coefficients are both 1s, right? So 1 over 1 tells me that that our horizontal asymptote is at y equals 1. Okay, now we can sketch those out. That's the easy part. We've identified the two asymptotes. Horizontal asymptote at 1, vertical asymptote at 2. Now we need to determine where our function is going to lie. Okay, so third step is to identify the x-intercept. And the way we determine our x-intercept is we find where f of x equals 0, which means we're going to set the numerator only equal to 0. So don't worry about the denominator, just the numerator. In this case, our numerator is x plus 1. Set it equal to 0. Solve for x. X equals negative 1. And this tells me that we have a point at negative 1, 0, our x-intercept. Then we're going to identify the y-intercept. And this happens where x is 0. So we're going to plug in 0 for x in the entire function. Okay, so if f of 0 equals 0 plus 1 over 0 minus 2, and this is 1 over negative 2, which is just negative 1/2, we have a y-intercept at 0, negative 1/2. So let's go ahead and plot these 2 points. Okay, point at negative 1, 0, and a point at 0, negative 1/2. Well, great, I have 2 points, but you can see this is only going to make up or the one piece of my function, right? I only have this section here. So if I go ahead and sketch this out, I have the bottom portion. So I know that my second piece is going to go somewhere up here, okay? You need to find a few points. So the way to do this, because we have an asymptote at 2, use the following coordinates, right? The x values. Whether you want to plug in 3, 4, and 5, it's up to you. Let's just find it in some extra points. That's our 5th step. And the way we're going to do this is we're simply going to plug in those extra values. So I'm going to use positive 3 and positive 4. Okay, you can use your calculators. Just take your function, type it in, substitute both x's with these values. If you substituted 3, you should have found 4 for y. And if we substitute in 4, you get 2.5. Okay, so I can go ahead and plot those points, 3, 4, and 4, 2.5, and sketch out my second piece of the function. Okay, now the more points you have, the better, of course. With simple rational functions, it was easy to plot just using 1 point, but in this case, you do need to find a couple of extras, especially if you don't have a point in the second region of the rational function. Okay. All right, let's go ahead and do B together as well, just so that you guys can see or follow along as we go through all of these steps. Okay, step 1, vertical asymptotes and holes. Now, our function is not in a factored form, so we do need to go ahead and factor this. And if we look at the numerator, x squared plus x minus 2, and you do diamond, remember if you need to go ahead and write it down, write it down. Just press pause, it's that easy. So we have negative 2 up top, 1 on the bottom, multiplies to negative 2 and adds to positive 1, would be positive 2 and negative 1 over x plus 3. Okay, now nothing canceled out, so I know I'm not going to have any holes. All I have is a vertical asymptote at x equals negative 3. Now, step 2, horizontal or slant asymptotes. Based on the degree is greater on top than it is at the bottom, so we need to perform division. Okay, so if you need to make a note of that, 2 is greater than 1, so we're going to perform our long division here. We have x squared plus x minus 2 divided by x plus 3, so we know we're going to have a slant asymptote. Okay, x squared divided by x is x, multiply it, we get x squared plus 3x, change signs, perform the operation, and we have negative 2x minus 2. Again, divide negative 2x by x, and we get negative 2. Multiply, negative 2 times x is negative 2x minus 6. Change our signs, and we get positive 4 as a remainder. Our remainder does not matter. Remember, all we're looking for is the quotient here. So we have a slant asymptote at y equals x minus 2. Okay, let's go ahead and graph these asymptotes to begin with. So x equals negative 3. And slant asymptote at y equals x minus 2. Now, if you don't remember how to graph this, y equals mx plus b, we always start at the y-intercept. So we're starting at negative 2, and we have a slope of 1, so up 1 over 1, right? So let's see, y-intercept of negative 2, using our slope, up 1 over 1, opposite direction, down 1 to the left 1. You can see our diagonal line here. Make your dashes, and you have your slant asymptote. Okay, now we still have 4 different regions. We have this region, this one, and this one. We need to determine where our function is going to go. So, third step, x and y intercepts. Let's start with our x-intercept by setting our function, our numerator equal to 0. Now in this case, because we already factored it out, it's easier to use the factored form, x plus 2, x minus 1, because in order to solve for x, all we're doing is applying zero product property. So we have x equals negative 2 and x equals positive 1. This means we have 2 x-intercepts for this function. We're going to have a point at negative 2, 0 and 1, 0. Y-intercept, we're going to substitute 0 for all the x's. So if I do 0 plus 2 times 0 minus 1 divided by 0 plus 3 and simplify, I get 2 times negative 1 over 3, which is negative 2/3. So we have a y-intercept at 0, negative 2/3. Okay, let's go ahead and graph those points. Negative 2, 0 is up here, 1, 0, and 0, negative 2/3. It's approximately right here. Connect these points. Remember, curve towards the asymptotes. Here's my first part of the function, right? Where's the second part? Well, I'm on the right side of my vertical asymptote, so I'm going to go ahead and use points from the left side to determine if my function, the second piece of my function, is going to be up here or if it's going to be at the bottom, okay? So extra points always. That's step number 5. All right, so let's go ahead and substitute negative 4, negative 5, and I'm just going to go ahead and do negative 6 as well. If you plugged in those values, you should have found negative 10 for negative 4, negative 9 for negative 5, and negative 1/3 for negative 6. So plot those points. We're at negative 4, 10, negative 10, negative 5, negative 9, and negative 6, negative 9 1/3, so about right there. Connect your points smoothly towards your asymptotes, and you have your function. All right, so go ahead and try C and D, okay, all 5 steps. Vertical asymptotes, holes, slant asymptotes or horizontal asymptote, x-intercept, y-intercept, extra points, graph them, and then come back and check your work.